15.7 covers Le Chatelier's principle. This is different because what we have already been working with is Q versus K, working with initial concentration and going to equilibrium. With Le Chatelier, we're already at equilibrium and we're going to alter it. So that means we're going to do something to push this system out of equilibrium. Then we're going to figure out what this is going to do to the system. So if a system is at equilibrium and it's disturbed by a change in temperature, pressure, or the concentration of one of the components, the system will shift its equilibrium's position so as to counteract the effect of the disturbance. This has become very important in the agriculture industry. This is a way to mass produce ammonia, NH3, which is a big portion of fertilizers. When it was realized that if you could change your pressure, change your temperature, and mess with the equilibrium, this was applied to the Haber process. If you increase the pressure, the amount of ammonia, NH3 present, at equilibrium would increase. So if you increase the temperature, the amount of ammonia at equilibrium decreases. It was realized the ideal conditions for making ammonia from nitrogen and hydrogen gas at low temperature, high pressure, would greatly increase your ammonia because you keep pushing the equilibrium towards the products. So the Haber process is basically looking at the transformation of nitrogen and hydrogen into ammonia, NH3, and this is a tremendous significance in agriculture where you have ammonia-based fertilizers, which are very, very important. So this is your equation where you have one diatomic nitrogen, 3 diatomic hydrogens are going to produce 2 ammonias. So if you add hydrogen to the system, nitrogen will be consumed and 2 reagents will form. So you're going to end up with more NH3 or ammonia. So basically, if you are increasing one of the reactants, so in this case we're adding more hydrogen gas, it can react with the nitrogen and make more of the product. So if you put more of the reactants in, it's going to push the equilibrium towards the products. Okay. Now we're going to be making more of your products. We have to watch though because we are limited in the amount of nitrogen that we have. However, this really isn't a problem because we just need to gather more from the air because 78% of our air is made up of nitrogen gas. So this is the apparatus that helps push the equilibrium to the right by removing the NH3 from the system as a liquid. So another way that we can make more ammonia instead of increasing a reactant is we can remove the product. So let's go back to this slide here. So this time when we remove the product, remove the NH3, the only way the reaction can go is back towards, again, the product side. So it's going to force the reaction of your nitrogen and your hydrogen to make your 2 molecules of NH3. There is no NH3 to go back to break down to nitrogen and hydrogen. So if you keep pulling out your ammonia, it's going to force the nitrogen and hydrogen to keep making NH3. Typically, a lot of NH3 is not made naturally. So this is a way to force the reaction to go into that direction towards the products by pulling out the product as it's formed. So like I mentioned, this is your apparatus that's going to basically recycle unused nitrogen and hydrogen and make ammonia as the reaction occurs. So effects of volume and pressure changes. Le Chatelier's principle predicts that if pressure is increased, the system will shift to counteract the increase. That is, the system shifts to remove gases and decreases the pressure. So a system is going to attempt to be under the least amount of pressure as possible. An increase in pressure favors the direction that has fewer moles of a gas. And we will look at a sample problem where we're looking at the shifting due to fewer number of moles. In a reaction with the same number of moles of gas in the products and reactants, changing the pressure has no effect on the equilibrium. No change will occur if we increase the total gas pressure by the addition of gas that is not involved in the reaction. So it has to be a specific type of change. So the effect of changes in temperature on equilibrium. So in equilibrium, you can increase or decrease the temperature. So in this example here, notice we have this color change of your cobalt chloride complex ion from blue to pink, okay? And back and forth, then from pink back to blue, okay? So it's gonna go from blue to pink. So in this case, we have taken the solution and we have placed it into the water, and it's gone from blue until pink, and we can go back and forth. If we add it to hot water, we're going to go from pink back into blue. So the two complex ions that we're working with is the COH2O6. This is going to be your pink, and the COCl4, and this is going to be your blue. This is what's formed during your equilibrium reaction. One way to change equilibrium is to add HCl, an acid, or water. So if you add extra water, you're going to form this ion over here, the COH2O6. And it's going to turn pink. If you add more or add HCl, that means you're adding more chloride ions, or more chloride ions are available, and you're going to end up forming this complex ion, the COCl4, and it's going to turn blue, okay? A second way is by changing the temperature. So notice that delta H is greater than 0. So what type of reaction is this? This is an endothermic reaction because it has a positive delta H. So could I say that heat is one of my reactants? Yes, I can, okay? For an endothermic reaction, heat needs to be added for the reaction to occur. If adding a reactant to your reactants would push your equilibrium towards your products. Okay, so if we add heat, because heat is one of our reactants here, it's going to push our equilibrium towards the products. So that means that we're going to have more COCl2 and water. If we end up adding heat, it's going to turn blue. So we can put this test tube, because again, there's going to be more COCl4 here in this complex ion in this case. Now, if we put this test tube back in water, we'll now be removing our reactant. Okay, so we're going to be removing our heat, which is going to push the equilibrium now back towards the reactant side. So now you're going to have COH2O6 plus your 4 chloride ions. There's going to be now more of your COH2O6 complex, and it's going to turn pink. We're actually going to be working a lab where we're going to be looking at different color changes and mess with their equilibriums by looking at the color changes. So basically, the three basic things that you can do to change your equilibrium or mess with your equilibrium is to change the concentration of your reactants or products, change the temperature, or if we're talking about gases, we can change the pressure. In this reaction here, we have a change in pressure over the reaction is not going to do much for it, okay? Because notice these are all aqueous, okay, and a liquid. So if you have a gas reaction, a change in pressure will have an effect on your equilibrium. Okay, we're going to look at sample exercise 15.3 on page 636. It says, consider the following equilibrium. N2O4 equilibrium to 2NO2, and you have a positive delta H is 58.0 kilojoules. In what direction will the equilibrium shift when each of the following changes is made to a system at equilibrium? Okay, so in A, this time we're going to be adding into O4. So how is this going to shift your equilibrium? Where is it going to push your equilibrium? If we're adding more of our reactant, in this case, it's going to shift it to the right, okay? What if we remove NO2? So we're going to be removing part of our product. So that means now it's still going to shift to the right, okay, because I'm pulling out my product and more product's going to be formed because there isn't any product to go back to your reactant, okay? What if we increase the total pressure by adding N2 gas? Okay, so is N2 gas part of our reaction? No, this is a totally different gas that's not a part of this equilibrium. So it's not going to affect anything, okay? We're going to have the same partial pressure of each of the gases in this equilibrium. That's in the reaction itself. So adding N2 is going to do nothing to the equilibrium. There's going to be no shifting. Even if this was a closed container, we are going to increase the total pressure, but we're not increasing the pressure of either of the two gases, N2O4 or NO2. D, increase the volume. Okay, so if we increase the volume, we're going to decrease the pressure of the gases. Now, what did we do to the partial pressure of N2O4 and NO2? So it's going to be kind of hard to think about decreasing pressure. So let's think about the opposite for a moment. Let's say we increase the pressure of N2O4 and NO2. Which way will the equilibrium shift if we increase the pressure by decreasing the volume of the container? So basically we're going to be compressing the gases. So it's going to shift the equilibrium to the left because there are less moles of a gas on your reactant side. So your equilibrium is going to shift to decrease the pressure as much as possible. When you increase the pressure, the reaction will shift to the left because there is 1 mole of gas bouncing around versus 2 molecules bouncing around that you have on your product side. So now let's go back to D. If we increase the volume, it's going to shift the equilibrium in the other direction here. So it's going to shift it to the right. and E if we decrease the temperature. So think about this. Where is the heat? Okay, this is an endothermic reaction, so that means that it has to be part of your reactants over here. So if we decrease the temperature, think about what happens when we remove a reactant, remove our heat. So which way does that push the equilibrium? That means it's going to push it towards the reactant side. So looking at this same example up here, instead of the question being, say, what direction will the equilibrium shift? What if the question asks you, how will the change in the equilibrium, or how will it change the equilibrium constant, K? Remember, the only thing that changes your equilibrium constant is going to be temperature. Why is this? Remember, K is the ratio of the rate constants, the forward and reverse rate constant. Those rate constants also are going to change with temperature. So that is why the equilibrium constant is affected by temperature. Thus, K actually changes when you change the temperature for the rest of the changes that we mentioned up here, adding or reactant or product, or removing a reactant or product, increasing your pressure or volume. These are not going to affect K. They only change the concentration ratio of your reactants and your products. However, with the temperature change, we're also changing K. So how would this change K? If the equilibrium is going to shift to the left for E, like we have right up here, a decrease in temperature is going to shift towards the reactants. So let's look at the equilibrium expression. Okay, so here's our equilibrium expression for this equation. We're going to end up with more reactant. So what is this going to do to our K value? That means we're going to have a decrease in K, so it's going to go down. So if they ask what happens to K when we decrease the temperature, okay, there's really not one correct answer because it's going to depend on if the reaction is endothermic or exothermic. So that's what you have to watch out for here. So in an exothermic reaction, the arrow would be pointing in the other direction. So that means that the equilibrium would shift the equilibrium towards the products because heat is now a part of your products. So we could write heat over here. So that would mean that we would have to have a negative delta H. So a decrease in temperature, the equilibrium would shift towards the products because it would be like removing a product. So if you pull out a product, it's going to shift the equilibrium towards the product side. So again, we're going to look at the same equilibrium expression here. We have more products, which means we're going to have an increase in K. So if you decrease the temperature of an exothermic reaction, you're going to increase K. So we're going to look at sample exercise 1514 on page 637. It says using the standard heat of formation data in Appendix C, this is located in the back of your book, determine the standard enthalpy change for the reaction. So basically it's just an additional step where we find the standard enthalpy change. And remember that the standard heat of formation would be forming 1 mole of the product. But how many moles of our product do we have? We have 2, so we looked up this number in the back, and that means we'd have to multiply this by 2 to get our answer, okay? This is still an so if it's still exothermic, this is going to shift your equilibrium towards the products. So if we decrease the temperature, it will push the equilibrium towards the products. Is this consistent with the factors that we mentioned at the beginning of the video and with the Haber process? Because remember, we said the Haber process works best at lower temperatures, so this does make sense. So this means this is an exothermic reaction, and you do have a decrease in temperature. It's going to push the equilibrium towards your ammonia, and this is what we want. Now, if we increase the pressure, which direction will the equilibrium go? It's going to go to the side with your least number of moles. So it's going to be your product side, because we, again, have 2 moles over here and 4 moles on our reactant side. So now let's briefly touch upon catalyst. Okay, so a catalyst increases the rate of both the forward and the reverse reactions. So it's going to help you get to the equilibrium faster. A catalyst will not affect the position of your equilibrium, so it's not going to change your equilibrium constant. Okay, or K. So how would K change? The equilibrium is, I got thrown off there because of that, so I apologize. Let's just back up and start over with a catalyst. A catalyst increases the rate of both the forward and the reverse reaction. So basically it's going to help you get to equilibrium faster. So it's not going to affect the position of your equilibrium, and it's not going to change your equilibrium constant, or K. Okay. It's not going to change the concentration you're going to end up with at the end. Okay, so a catalyst is going to help both reactions happen faster, both your forward and your reverse. It just helps the reactions reach equilibrium more quickly, is what you can think about. Okay. And this is basically kind of what I just said. When one uses a catalyst, equilibrium is achieved faster, but the equilibrium constant composition remains unaltered. So now I want to look at the AP curriculum, and during Understanding 6B, systems at equilibrium are responsive to external perturbations, with the response to leading to a change in the composition of a system. Okay, so perturb means you're going to bother the system in some way. So you can change the rate of the forward and the reverse reaction. This is ultimately going to cause your change. So you're going to cause a change in your rates to fall out of balance. This is going to be called a stress, or cause stress on the system. So the system is temporarily out of equilibrium. The system's going to work to get back to the equilibrium state again. And this refers to that shift of your chemical reaction. So when I say it is shifting to the right or shifting to the left of the equilibrium, this is what I'm really meaning. It's affecting those reaction rates, causing them to be out of balance temporarily until they come back into balance. If we look at 6B2, okay, it says a disturbance to a system at equilibrium causes Q to differ by K. So it says thereby taking the system out of the original equilibrium state. So think of this as Q versus K as well. Okay, the system responds by bringing Q back into agreement with K, thereby establishing a new equilibrium state. And finally, let's take a look at B. In some stresses, such as changes in concentration, causes a change in Q. Okay, so a change in the concentration by adding a reactant, this is going to change Q. It's going to work to get it back to K. Now, if you change your temperature, this changes K. Now, Q and K are going to be different because the K has changed. So the reaction will shift in either way to bring Q and K back to equality.